Hello, this is Dr. Hanaa Assil, and this is a chapter in the IA2 Chemistry at Excel. This is about acid-base equilibria. So, first of all, let us take a look at definition of an acid. According to Bronsted-Lowry, an acid is a proton donor. That means that when it dissolves in water, it gives H plus ions. So it is giving H plus ions to a base. Proton in this case is what we call H plus ions because the hydrogen atom is made up of just a proton and an electron. So if we talk about H plus, that means it is the hydrogen that has lost an electron. So it is just an atom that has only a proton. So we refer to it as a proton. So we say that an acid is something that gives H plus ion. So we refer to it as a proton donor. A base is what accepts this proton or this H plus ion. So for example, if I'm doing HCl plus H2O, what is happening is the HCl has changed to Cl minus. That means it has given up its H plus. That means it's an acid. Now the H2O in this case has accepted the H plus ions and become H3O plus hydronium ion. In this case, water is a base. We could have strong acid, and a strong acid is an acid that dissociates completely to give a lot of H plus ions. So nitric acid, hydrochloric acid, the sulfuric acid are all regarded as strong acids. This is because when dissolved in water, they will dissociate completely to give H plus ions and nitrate ions. But some acids are weak. So a weak acid is one that dissociates only partially to give a low concentration of H plus ions. For example, ethanoic acid is referred to as a weak acid. This is because when I dissolve ethanoic acid in water, not all the molecules will dissociate to give H plus ions. Only a small number of the molecules will dissociate. So we have lower concentration of H plus ions, so we call this a weak acid. An amphoteric substance is one that can act both as an acid and as a base. For example, water is an example of an amphoteric substance. This is because when water reacts with an acid, it acts as a base. So in this case, the H2O took the H plus and became H3O plus, so it's a base. It's a proton acceptor. But in a reaction with a base, the water would act as an acid. So in this case, it is the water that gives up the H plus ion, so it is a proton donor. So in this case, it is an acid. If we have a reversible reaction, and you know that a reversible reaction is one that can go both forward and backward. Now, this is a reaction between H2O and NH3, water and ammonia. Now, going forward, the water donates H plus ions. So it changes from H2O to OH minus, and that means it has given up its H plus ions. We call it the conjugate base. It has become a base. Now, in the forward reaction, the ammonia is acting as a base because the ammonia accepts H plus ions from water and becomes NH4 plus. So we call the NH4 plus conjugate acid. This is because when we go backward, then the NH4 plus will give up its H plus ion, so it will act as an acid, and the hydroxide ion will gain an H plus ion, so it acts as a base. Let's take a look at some of the questions. When concentrated nitric acid and sulfuric acid are mixed, the reaction is this. In this reaction, the Bronsted-Lowry acids are which one? Which of these are acting as an acid? Can you see that the sulfuric acid going forward gives up H plus, so that is an acid. If I'm looking at the backward reaction, then the H2NO3 plus is the one that lost an H plus ion, and that is an acid. So this two, H2SO4 and H2NO3 plus, are acids in this case. When ethanoic acid is mixed with water, what are the Bronsted-Lowry conjugate acid-base pairs? Okay, so we have ethanoic acid plus water to give H3O plus CH3COO minus. Remember, if we're going forward, the one that is an acid will become a base, and the one that's a base will become an acid. So the CH3COOH is an acid. It gives off its H plus ions and becomes CH3COO minus. The H2O is the one that accepts H plus ions from the CH3COOH, so that's a base. So this is acid plus base to give what? The H3O plus is now the acid because water was a base, it changed into H3O plus, so now it's an acid. The CH3COOH was an acid, then it becomes a base. So notice that if we give up H plus ions, that's an acid. Now going backward, it is the H3O plus that loses an H plus, so that is my acid in this case, so my reaction is, or my answer is C. Okay, are we following? The following equilibrium occurs in liquid ammonia. What is the Bronsted-Lowry acid in this case? He says 2 ammonia. 2 ammonia means I have ammonia reacting with ammonia. Now one of them is going to give up the H plus ions, and one of them is going to gain the H plus ions. So the NH3, one of the NH3s, will give up H plus and become NH2 minus, so it's acting as an acid. But then going backward, it is the NH4 plus that will give up its proton to give ammonia, so that is the other acid. Now, we should know something about the water dissociation constants. You should know that water ionizes to form hydronium ion and hydroxide ion. Now, in water, the concentration of hydronium ion is found to be 10 to the minus 7. It is the same as concentration of H plus ions, so that is the H plus ions in solution. The concentration of hydroxide ion is 10 to the minus 7, and they found that if we are talking about the ionic product of water, the ionic product of water is the concentration of H plus ions multiplied by the concentration of OH minus, so Kw is 10 to the minus 14. You should know that pKw is minus log. The P of something is minus log of it. So the P of the ionic product is minus log of that number. You should also know that pH is minus log concentration of H plus ions. These are the equations that you're supposed to learn. So if we have in water a neutral solution, the pH is minus log H plus ions. We said that the concentration of H plus ions is 10 to the minus 7. So minus log of 10 to the minus 7 is 7. Okay, this is math or calculator. The minus log of 10 to the minus something is that number. So that is why we say that the pH of water is 7. The pOH is minus log of concentration of hydroxide ions. So if I have water, the concentration of hydroxide ions we said is 10 to the minus 7. Minus log of that also is 7. So in neutral solution, the pH plus the pOH is 14. So if you're given one, you can get the other. The total of pH and pOHs should be 14. Okay, let's look at this question. What is the pH of a solution of sodium hydroxide with concentration 1 times 10 to the minus 3? Well, sodium hydroxide is a strong base, so it ionizes completely to give Na plus and OH minus, and that means that the concentration of sodium hydroxide is the concentration of hydroxide ions. So we know now that the concentration of hydroxide ions is 1 times 10 to the minus 3. He is asking for pH. But I should know that concentration of H plus times concentration of OH minus is 10 to the minus 14. So I can get concentration of H plus ions. Now, once I know the concentration of H plus ions, you know that pH is minus log concentration of H plus ions. So the minus log of 10 to the minus 11 is 11. To calculate H plus ions from pH, we said the pH is minus log concentration. The concentration is 10 to the minus pH. So, for example, determine the H plus concentration of H plus ions of a solution. Remember that the squared bracket in all of these cases means concentration. So concentration of H plus ions of a solution that has pH of 4. So if my pH is 4, what is the concentration of H plus ions? We said that will be 10 to the minus pH. So it is 10 to the minus 4. Okay, another question. Define the term Bronsted-Lowry acid. How did we define that? Acid is a proton donor. What is the pH of 0.1 mole per decimeter cubed solution of hydrochloric acid? How would the pH of any weak acid of the same concentration differ from the pH of hydrochloric acid? Okay, pH of hydrochloric acid with 0.1 mole per decimeter cubed. We said the pH is minus log concentration of H plus ions. Remember that hydrochloric acid is a strong acid, so the concentration of the acid is the same as the concentration of H plus ions. pH is minus log concentration, so that is minus log of 0.1, and that is equal to 1. So the pH of hydrochloric acid is 1. Now, how would that differ from the pH of a weak acid? Well, you should know that the pH of the weak acid would be higher than 1. It will be 3, 4, 5. Weak acid has a higher pH than a strong acid. At 18 degrees Celsius, the ionic product of water is this. At this temperature, water is what? Neutral, alkaline, what? He gives me Kw, and you know that Kw is concentration of H plus times OH minus, and that is the number that he gives me, and that means I can get concentration of H plus ions, because H plus and OH minus are the same, so that is square root of 6.4 times 10 minus 15. So now that I have the concentration of H plus ions, then the pH is minus the log of that, and that comes out to be 7.1. Now remember, 7.1 is neutral or alkaline. We regard it as neutral. This question says, what is the pH of a 0.1 mole per decimeter cubed solution of barium hydroxide? And he gives me the pKw. You should know the pKw is 14. Barium hydroxide, when it ionizes, 1 mole of barium hydroxide gives 2 moles of hydroxide ions, and that means the concentration of the barium hydroxide, if it is 0.1, then the concentration of hydroxide ions would be twice of that. Now, the pKw I can use to get Kw. Kw is 10 to the minus pKw, 10 to the minus 14. That is H plus times concentration of H plus ions times concentration of hydroxide. So I can use that to get the concentration of H plus ions, which would be 10 to the minus 14 over concentration of hydroxide, which is 0.2. I have this value for concentration of H plus ions, so I can use it to get the pH. We know that the pH is minus log concentration, so that would be 13 point. Okay. Calculate the pH of an aqueous solution of hydrochloric acid of concentration 0.4 mole per decimeter cubed. Okay, we should know that hydrochloric acid is strong acid, so we said the concentration of the acid is the same as the concentration of H plus ions, and that means I can get pH is minus log the concentration, so that comes out to be 0.4. Straightforward, right? Okay, the pH of a sample of water is 7. 10 centimeter cubed of 1 mole per decimeter cubed hydrochloric acid is added to 990 centimeter cubed of this water. What is the pH of the solution formed? Okay, so he's saying the original pH of the sample of water is 7. You're going to add 10 centimeter cubed of 1 mole per decimeter cubed hydrochloric acid to 990 centimeter cubed of the water. So the number of moles of HCl that you have in solution is what? We said number of moles is concentration times volume, and the volume has to be in decimeter cubed, so it is 1 times 0.01, so my number of moles is 0.01. Now, the total volume is 990 plus the 10 centimeter cubed of hydrochloric acid. So my total volume is 1 decimeter cubed, and that means the concentration of H plus ions, you know that concentration would be number of moles over volume. So this is my concentration of H plus ions. To get pH, it is minus log of that. So the pH of my solution is 2. A solution of sodium hydroxide of concentration this has a pH of what? So the concentration of sodium hydroxide solution he gives me is 0.008, and he wants its pH. So sodium hydroxide is a strong base. The concentration of hydroxide ion is the same as the sodium hydroxide, so here it is 0.008. We know that concentration of H plus times OH minus is 10 to the minus 14. So the H plus ions alone is 10 to the minus 14 over the concentration of OH minus, and the pH is minus log of that. And this comes out to be 11.9, so my answer is C. Which solution has the highest pH? We have different solutions here. First of all, to have a higher pH, it has to be a stronger base. So is it sodium hydroxide or ammonia? It has to be sodium hydroxide that will have a higher pH. Now, which one would have a higher pH? 0.01 mole per decimeter cubed or 0.1? Of course, the more concentrated the solution, then the higher or stronger the base is. So it will have a higher pH. An aqueous solution contains 4 grams of sodium hydroxide in 250 centimeter cubed of solution, and he wants me to get the pH of the solution. Again, first thing we do is number of moles of sodium hydroxide. In this case, it will be mass over molecular mass. The mass is 4 over the molecular mass that he gives me. That means I have 0.1 mole. Now, I can get the concentration of hydroxide ions because that will be number of moles over volume. And remember to change the volume to decimeter cube by dividing by 1,000. So the concentration of OH minus ions is 0.4. I know that H plus times OH minus is 10 to the minus 14. So I can get the concentration of H plus ions. pH would be minus log of that, and that comes out to be 13.6. Ka. Ka is the acid dissociation constant, and this happens for a weak acid. We said if I have a strong acid, it dissociates completely, so the concentration of H plus ions would be the same as the concentration of the acid. But for a weak acid, it dissociates partially, so only some of the acid will give up H plus ions, and the equilibrium constant for the weak acid dissociation is called the acid dissociation constant, Ka. So Ka is concentration of products over reactants, so it's concentration of H plus times A minus over the original concentration of the acid. The greater the amount of dissociation, the larger the value of Ka. So remember that a higher value of Ka means more acidic solution. pKa is minus log of Ka, and the Ka is 10 to the minus of pKa. And please remember this new equation: the concentration of H plus ions is the square root of Ka times concentration. Okay, so the concentration of the H plus ions, remember we're talking about a weak acid, is the square root of the Ka times the concentration of the acid. Okay, here he says methanoic acid was mixed with propanoic acid. Which acid is stronger? We said if I look at the Ka or the pKa, remember that the one that has higher Ka is a stronger acid, or lower pKa. Higher Ka or lower pKa is the stronger acid. So the stronger acid is the one that will dissociate to give H plus ions. So if I'm reacting methanoic acid with propanoic acid, it is the methanoic HCOOH that will give up its H plus ions, and it is the other one, the propanoic acid, that will gain the H plus ions. The equation for the reaction between a weak acid and strong base, which is sodium hydroxide, is this. The pH of the solution is most likely to be what? Now, if I mix a strong acid with, a strong base with a weak acid, we have a strong base, which is sodium hydroxide, with a weak acid. What do you think the pH of the solution would be? Remember that the higher the pH, the more basic, or the stronger the base. So sodium hydroxide would have a pH of about 13 or 14. Now the weak acid, which is represented here by HX, the weak acid would have probably a pH of 4 or 5 or 6. So if I mix them together, my average pH, or my overall pH, would be somewhere around 8.5. A solution of the weak acid, ethanoic acid, is diluted from 0.1 mole per decimeter cube to 0.01. What happens to the pH? Now, what is happening? He is diluting it. This is a weak acid, and we are diluting it. Remember that that will make it even weaker, so the pH would increase. And if I diluted more, then more of it will dissolve and form H plus ions, and that means the proportion of ethanoic acid molecules that dissociate would increase. Are we following this? We're talking about a weak acid. Carbonic acid is a weak acid which dissociates in 2 stages, and he's saying write the expression for Ka. Remember that the Ka is always the products over the reactants. Water as a liquid is regarded as very high concentration that it would not affect, so we do not include it in the Ka. So the Ka for the first stage is the concentration of the product over the concentration of H2CO3. Now for the second one also, it is the concentration of the products over the concentration of HCO3 minus. Again, we ignore the concentration of H2O because basically it does not change. A solution of carbonic acid has an initial concentration of 0.1, and he gives me the Ka. Use Ka1 to calculate the equilibrium concentration in mole per decimeter cubed of the hydrogen carbonate ions. So this is the equation he gave before: carbonic acid plus water to give H3O plus HCO3 minus. He said that we're starting with initial concentration of 0.1. So the carbonic acid is 0.1, the others are 0. When we react, part of the carbonic acid dissociates to give H3O plus and HCO3 minus. At equilibrium, we have the rest of what has remained of the carbonic acid, so that is 0.1 minus X, to give X of each of the products. Remember that for a weak acid, the value of X is actually very small. Only a very small part of carbonic acid will dissociate. So to simplify matters, we regard the 0.1 minus X as approximately 0.1, so that when we put these numbers into the Ka expression for Ka, then the carbonic acid will dissociate to give H3O plus, which is X, times HCO3 minus, which is another X, so that's X squared, over the carbonic acid we said we're going to say is approximately 0.1. He gives me the value of this as 4.17 times 10 to the minus 7. That means I can use it to get X. X will be the square root of the 0.1 times the Ka. This is the value of X, which is the value of the H3O plus concentration. So the pH is minus log the concentration of H3O plus, and that means my pH is 3.7. Okay. State the 3 assumptions we have made in your calculation. So when he gives me these equations and we calculated the concentration of H plus ions, what are the assumptions that we made? You should realize we said, first of all, that the dissociation of carbonic acid is negligible. So the concentration of H2CO3 at equilibrium is basically the same. That's one assumption. The other assumption is that the H plus ions from dissociation of water is negligible. So the H plus, the concentration of H3O plus, or the concentration of H plus ions, we regard it as the same as the concentration of HCO3 minus, as if the H plus came only from the carbonic, not carbonic and the dissociation of water. Ka2 is much smaller than Ka1, and so any further dissociation of the HCO3 minus is regarded as negligible. These are assumptions that are made when we have a series of equilibria for the dissociation of an acid that has 2 protons. Remember that in this case, we're talking about an acid that has 2 protons. So first it gives up its first proton, and then it gives up its second proton. Okay, we follow this using titration graphs. So pH is measured using a pH meter as we do titration. A graph to show the change of pH during the titration is as follows. You remember what's titration? We have a certain base in a flask and we're adding acid to the flask. So if we're titrating a strong acid with a strong base, the first thing we're doing is we have a base in the flask, so it's a base, so it has a high pH. So we're starting from pH at point A. And then as I add acid, the pH of the solution decreases until at point B, the solution has been neutralized. So this is known as the equivalence point. And this is where an indicator that is present would change color. Then, after that, any more acid that is added would lower the pH further until the acid is excess. So, the pH of the flask would be the pH of the excess acid, which is at C. Are we following this? So, this is called a titration curve in which we're following the change of pH as we titrate an acid with a base. Now, this information is present in your data booklet. You would be given a data booklet with your exam paper. One of the pages shows the indicators, so you don't need to sit down and memorize all of these pH ranges. You already have this list in front of you. And the point is, the indicator that you choose for a certain titration should be the one in which the color changes at about the pH of equivalence. So let's take a look. If I'm titrating a strong acid with a strong base, we said we start at very high pH, and then at the neutral point or at equivalence point, the solution is neutralized, and then any more acid that is added causes the pH to be very low. Where is my equivalence point here? It's about pH 7. Can you see that? So you look at your list of indicators and you choose the indicator that will change color in that pH range. So you're looking for something that will change color in the range of 7. So if you look at bromothymol blue, it changes color between 6 and 7.6. So this would be a suitable indicator to be used in this titration. So remember, we're titrating strong acid with strong base. The equivalence point is at around pH 7. The suitable indicator would be bromothymol blue. What if I'm titrating strong acid with weak base? So this would be the kind of titration curve that you will have. So we're starting with a weak base, so the pH is about what, 10, 11. As I add the acid, it will decrease until it is neutralized, and then the extra acid would cause the pH to become very low. Where is my equivalence point? It's about maybe 4 or 5. 4 point something or 5. So I look at the data booklet, which indicator would be suitable to change color at around 4 point something. So this is methyl orange. So remember, when we are titrating a strong acid with a weak base, the equivalence point is lower than 7, around 4 point something. So that would be methyl orange would be a suitable indicator for that. What if I'm titrating a weak acid with a strong base? The strong base starts with a high pH. The weak acid, remember that it is the solution is neutralized, and then you're still adding a weak acid, so your final pH is around 4. That is the pH of a weak acid. So where is my equivalence point? It's at around 9. I look for the indicator that would change color in that pH range, so that is phenolphthalein. So remember that phenolphthalein is a suitable indicator for a titration in which I have a weak acid with a strong base. What if I'm titrating a weak acid with a weak base? Problem is, there is no sharp decrease in pH at a certain point, so there is no clear equivalence point, and that means no acid-base indicator is suitable since the color change will be gradual. So this is a summary of what we just said. Bromothymol blue is suitable if you're using strong acid with strong base. Phenolphthalein you can use if we are titrating weak acid with strong base. Methyl orange would be the suitable one if I'm titrating strong acid with weak base. What if I have a diprotic acid? Diprotic acid is an acid that has 2 H plus ions that it can give up. So if I'm titrating, for example, sulfuric acid with a strong base, first it will give up its first H plus ions, then it will give up its second H plus ions. So in this case, the number of bumps in the graph is the same as the number of H plus ions. So looking at the graph, I can tell that this is a diprotic acid. Also, if I have a base like diamine, it has 2 parts that can accept H plus ions. It has 2 nitrogen atoms that can accept H plus ions. So that means that it will accept H plus ions first, and then the other nitrogen would accept the other H plus ions. So you'll have also two bumps, but in this case, we have a base, so the pH is high, and we're titrating it with the acid. So this is a summary of the graphs. Please understand it, then you will be able to remember it. So let's take a look at some questions. When 0.1 mole per decimeter cubed sodium hydroxide is titrated with 25 centimeter cubed of ethanoic acid. Again, sodium hydroxide is a strong base. Ethanoic acid is a weak acid. The best indicator would be what? We said we're titrating weak acid with strong base. So the weak acid means that the pH does not go that far down when you're titrating. You look for something that has the pH range above 7. So we said we use phenolphthalein as a suitable indicator. This question says which two solutions, both of concentration 0.1 mole per decimeter cubed, have been used to produce this titration curve. So let's take a look at this. This is something we're starting with a low pH, but this is not very low, so it is probably a weak acid, and it goes up to something that's near 14, so that would be a strong base. So we're looking for something that has a weak acid with a strong base, and that means this answer should be correct. Remember, methanoic acid is a weak acid. It would have a pH of about 4, that's right, and the KOH is a strong base with a high pH. This question says titrations were carried out using aqueous solutions with concentration 1 mole per decimeter cubed, and he has these titration curves, and he's asking which curve would be obtained for titration in which hydrochloric acid is added to aqueous ammonia. Well, let's take a look. These are our choices, and he's saying which of these is hydrochloric added to aqueous ammonia. Remember that aqueous ammonia is a weak base, so it has to start with something around 9 or 10, pH 9 or pH 10. So which one starts with around pH 9 or pH 10? That's it, 11 or about. And I'm adding hydrochloric acid, which is a strong acid, so I should end up with a very low pH. So that first one is my correct answer. For which titration would methyl orange not be a suitable indicator? Now, we look at the data booklet and we find that the methyl orange has a pH of pH range of 3.2 to 4.4. So which of these would not be suitable for methyl orange? Which of these has its pH of equivalence not suitable for methyl orange? This one has a pH of about 9 for its equivalence, so that is too high. We cannot use methyl orange for this. We could use it for the others. You will find that the equivalence point may be around 4. This question says an example of a diprotic acid is cis-butene dioic acid. Titration of this acid using sodium hydroxide solution gave this titration curve. Which indicator would be the most suitable for measuring the endpoint of the neutralization of this with a pKa of 6.33? And he says you need to use your data booklet. Well, I look at the pH of equivalence and I find that it's around what? Around 9 point something. Which one of these indicators could be used for that? You can see that the phenolphthalein has a pH range of 8.2 to 10, so that would be the suitable indicator. This question says a graph of pH against volume of acid added for an acid-base titration is shown. Which acidic solution was used in this titration? Again, I look at the final pH. The final pH is about 1, so it has to be a concentrated acid. So A and B are wrong because they are talking about ethanoic. Ethanoic would never go down to about 1. pH 1. Now, I have a choice between 0.1 mole per decimeter cubed and 1 mole per decimeter cubed. Remember that pH is minus log concentration of H plus ions. So, if I choose C, then the pH would be minus log of 0.1, and that means the pH is 1. While if I choose D, the concentration, the pH would be minus log of 1, and that is 0. So my answer is C. Which basic solution was used in the titration? So this is the curve. Which basic solution was used in the titration? Well, we look at where did it start. It started at around 10. Which of these would have a pH of 10? Remember that ammonia is the only one in that list that is a weak base. The others will have a pH much higher than 10. Lithium hydroxide, barium hydroxide, sodium hydroxide, all of these are strong bases with very high pH. A student suggested 5 indicators that might be used in this titration. How many of these indicators would be suitable? Well, this is the pH range of the indicators that he's mentioning. I look at the graph and I choose where the pH of equivalence is. So this is around 5 point something or below 6. Which of these could be suitable? Well, thymol blue cannot. Its pH range is very low. Methyl orange, yes, it could be around 4 point something possible. Bromophenol blue 2.8 to 4.6, also within the range around 4. Bromo crystal green is also in the same range. Phenolphthalein is out of the range. It's 8.2 to 10, so that will not be suitable, so we choose C. Are we following? Getting easier? The graphs show the changes in pH during a series of titrations, and he's asking which graph has ethanoic acid as one of its reactants. You should know that ethanoic acid has a pH around 4 maybe. So which one has at some point a pH around 4? So graph 4 would be something in which I'm adding ethanoic acid to a flask. Which graph shows a solution that has an acidic pH at the endpoint? Okay. Which of these has acidic pH at the endpoint? Remember, the endpoint is the pH, the point of equivalence, and that is the part of the graph that you have a sharp drop or a sharp rise in the graph. So, which one sharply decreases or sharply increases at the acidic pH? If you look at this, this is around 7. If you look at this, it's about 7. If you look at this, this is acidic. So this is the one that we should choose. Okay, so graph 3 has a point of equivalence at around what, 5, pH 5. So that is the one that has acidic pH at its endpoint. Which indicator is suitable for the titration shown in graph 3? Well, this is graph 3, and we said the equivalence point is just below 6, maybe 5 point something. I look for which of these is suitable, and I find that bromocrystal green is a suitable indicator. An indicator with a pH range 3.8 to 5.4 is suitable for titration of what? Remember that 3.8 to 5.4, that is a strong acid with a weak base. So we're looking for strong acid with weak base. So that is that first one. Nitric acid is strong, ammonia is a weak base. Okay, this question says carbonic acid forms two types of salts, carbonates and hydrogen carbonates. A solution of sodium carbonate is titrated with hydrochloric acid. On the grid below, sketch the likely shape of the titration curve. Remember that we said the carbonates require 2 moles of H plus ions. 2 moles of H plus ions means it's a diprotic, and that means that the graph will have 2 bumps, first of all. Now, he's saying I have 10 centimeter cube of sodium carbonate with concentration this. The sodium carbonate has a pH of 11.3, and 40 centimeter cube of hydrochloric acid with concentration this is added. This is the graph that you should see. Now, why did we draw the graph like this? First of all, he said the sodium carbonate solution that I'm starting with has a pH of 11.3. So I have to start the graph on top at 11.3. And then the graph, we said the graph has 2 bumps because we have a diprotic, and he's saying it takes 2 moles of H plus ions. The final pH is minus log of the H plus ions. Now, he is saying that I have 0.1 mole per decimeter cubed of hydrochloric acid, so minus log of that is pH 1. So my graph should end at the end at pH 1. Number of moles of sodium carbonate is concentration times volume. He gives me concentration and volume. The number of moles of HCl needed, remember that we will need 2 of them, twice the moles of sodium carbonate. So this is the number of moles of HCl, and that means that the volume is number of moles over concentration, and that means that the volume is 0.02 decimeter cubed, which is 20 centimeter cubed. This is the volume at which you have the equivalence point. So this is where you have a sharp decrease of pH. Buffers are solutions that resist a change in pH. So there are solutions in which you add a little bit of acid, you add a little bit of base, the pH does not change. This is because they have weak acid and its conjugate base. The weak acid will neutralize any base, and the base would neutralize any acid. So, for example, a buffer would be a solution of ethanoic acid with sodium ethanoate. Now, ethanoic acid would dissociate partially to give a little bit of H plus ions. The sodium ethanoate ionizes completely to give CH3COO minus, the ethanoate ion. Now, if I have a buffer solution of these two, that means I have this reversible equation, and that means if I add H plus ions to this solution, you're adding H plus ions, which is a product, the reaction will, or the equilibrium will shift to the left. And that means that the added H plus ions will not really change the pH. Now, what if I add hydroxide ions, a little bit of a base to this buffer? Then the hydroxide ions would react with the acid, remove it, and that means that the equilibrium will shift to the right. And again, the overall pH is not really affected. Another buffer solution is made of aqueous ammonia and ammonium chloride. So the aqueous ammonia reacts with water in a reversible reaction to form ammonium ions and hydroxide ions, while the ammonium chloride ionizes completely to give NH plus and Cl minus. So if we add a little bit of base to this solution, then the hydroxide ions will be higher, so it will shift the equilibrium to the left. Again, it will not really affect the overall pH. What if I add acid to the solution? Then the acid will cause the equilibrium to shift to the right, and no overall or very little overall change in the pH. Remember that for buffers, the pKa is minus log Ka. This second equation is a new one. please learn it. This is for buffers. pH is equal to pKa plus log of concentration of A minus over HA. So it is log of concentration of the negative ion over the concentration of the acid. So let's take a look at this question. A buffer solution is made by mixing ethanoic acid with sodium ethanoate in a 3:1 mole ratio. And he gives me the Ka for ethanoic acid. What would be the pH of the buffer solution? Okay. The equation pH is equal to pKa plus log of A minus over HA. And remember that pKa is minus log of Ka. So I can use that to get the pH. So the pKa is minus log of the Ka that he gives me, plus the log of concentration of A minus over HA. He says it is a 3:1 ratio. So you don't really need an exact number. You could just say it's log 1 over 3. So the pH in this case comes out to be 4.3. Again, this question says a buffer solution contains ethanoic acid with concentration 0.1 mole per decimeter cubed and sodium ethanoate with concentration of 0.05. He gives me the Ka for ethanoic acid. What is the pH of this buffer solution? Again, pH is equal to pKa plus log of concentration of A minus over concentration of HA. The pKa is minus log of the Ka. So pH is the minus log of the Ka plus the log of concentration of A minus. The A minus in this case is the ethanoate ion over the concentration of HA, which is the concentration of the acid. So that's 0.1. This gives me a pH of 4.47. Another question, a solution containing HCN and KCN is a buffer. When a small amount of acid is added, the solution acts as a buffer because what? Remember that in this case, I have HCN is a weak acid. It will ionize in a reversible reaction. If I add H plus ions, this causes the equilibrium to move to the left or to shift to the left, and that means hydrogen ions combine with the cyanide ions to form HCN. Okay, then he says a titration was carried out by adding 0.1 mole per decimeter cubed of hydrochloric acid to 0.1 mole per decimeter cubed of aqueous ammonia. And he gives me a titration curve, and he says which region of the graph represents the most effective buffer solution. Well, you look at the part of the graph in which there is no sharp change in the pH, so that is region U. A buffer was made by mixing this of concentration, this with of sodium hydroxide and this of propanoic acid. Calculate the pH of this buffer solution, and he gives me the Ka. So in this case, I have this equation, the propanoic acid reacting with sodium hydroxide. Remember that propanoic acid is a weak acid. That means the Ka is concentration of products over reactants, and he gives me a value for the Ka. I can calculate number of moles of sodium hydroxide, concentration times the volume that is given, number of moles of acid added, concentration times volume. Of course, we're changing the volume to decimeter cubed by dividing by 1,000. So I have the number of moles. The number of moles of the salt formed, remember that the equation shows 1 mole of acid reacts with 1 mole of base to give 1 mole of the salt. So number of moles of base is 0.001. Then it will need only 0.001 of the acid to give 0.001 of the salt. The number of moles of the salt is 0.001. And that means the concentration of the salt is number of moles over the total volume. The number of moles is 0.01. Remember, the total volume is 20 centimeter cubed plus 20 centimeter cubed. So that's 40 centimeter cubed, which is 0.04 decimeter cubed. So now I have concentration of the propanoate ion, the number of moles of acid left in the mixture. What is the number of moles of acid left in the mixture? It is the rest of the 0.005 mole, so that is 0.004 mole of acid, and that means the concentration of the acid is this number of moles over the total volume, and that means I can get the concentration of H plus from the equation of Ka up there, where we said concentration of propanoate times concentration of H plus over concentration of the acid is equal to 1.3 times 10 to the minus 5. So the concentration of H plus ions is the Ka times concentration of acid over the concentration of the propanoate ion, and that means H plus concentration is this number, and that means I can get the pH, and that is minus log of the concentration, so that comes out to be 4.3. Okay. Explain how this solution acts as a buffer when a small amount of alkali is added. Again, we said if we have this kind of equation, the mixture contains a large amount of the weak acid and its salt. If we add OH minus ions, they will react with the H plus, removing it from solution, causing more acid to dissociate. So that means it shifts the equilibrium to the right. The pH does not change since the change in concentration of the salt and acid is very small. In our blood, we have buffers. We have things like hydrogen carbonate, hemoglobin, dihydrogen phosphate. All of these act as a buffer. We need to keep the pH of blood around 7.35 to 7.45. So we have these buffers in the blood. For example, the hydrogen carbonate ion can be used to maintain the pH in the blood to be constant. It has this kind of equation, carbon dioxide plus water to give H plus plus HCO3 minus. If H plus ions increases, if the concentration of H plus ions in the blood increases, then the equilibrium will shift to the left and form carbon dioxide, use up the H plus. And if the H plus ions concentration decreases, then the equilibrium will shift to the right, the H plus ions are formed, and the pH is restored. If the solution becomes alkaline, the extra OH minus is used up in this kind of reaction. So the OH minus will react with the bicarbonate or hydrogen carbonate ion to give carbonate plus water, and that removes the extra OH minus. So, for example, here he says sodium hydrogen carbonate is part of a buffer in the body that controls the pH of blood. Two of the equilibria involved in this process are shown. Use the equilibria to explain how the buffer keeps the pH of the blood nearly constant when a small increase in concentration of hydrogen ions occurs. Again, there is a large concentration of HCO3 minus. This reacts with any excess H plus ions, so the equilibrium moves to the right to use up the excess H plus ions. More H2CO3 is formed. The equilibrium too moves to the right also to form more carbon dioxide and water. pH of a blood sample was found to be 7.41. Calculate the ratio of concentration of HCO3 minus to H2CO3 in the blood sample. And he gives me the Ka. Remember that concentration of H plus is 10 to the minus pH. He gives me the pH as 7.41, so it's 10 to the minus 7.41, and that gives me the concentration of H plus ions. Now, in this equation, the Ka is equal to concentration of products over concentration of reactants. Again, we ignore the H2O, and that means I can use this to get the ratio. He wants the ratio of the concentration of HCO3 minus to H2CO3. That will be Ka over H plus, and that gives me this ratio. Thank you for listening. I hope this wasn't too long for you, and I hope it was useful. Thank you.